Right now, the goal of this lecture is to prove this theorem. Now we want to prove this theorem. And an important property of this theorem, of this, is that this, from the definition, it is not clear at all that this partition function is symmetric in the variables x's and y's. But it turns out that this partition function is symmetric in the variables x1 up to xn and symmetric in the variables y1 up to yn. In other words, if you change x1 and xi and xj, this does not change. Also, if you change yi, yj, does not change. But it's not clear at all. We will prove that first. And it's a very interesting proof. It's called Baxter's Yang-Baxter equation. So it's also called Baxter's triangle to triangle relation. So we in order to prove the formula for Zn, we will first prove this, that Zn is symmetric in x1 xn and symmetric in y1 yn. So recall, so the weight of the state, the weight of each state is defined by the product of their weight, the weight of each vertex. So weight of a state equal product of weight of all vertices. Right? And what is the weight of a vertex? The weight of a vertex is determined by the label of the vertex. The label, I mean Zij or xi over yj. Label of the vertex text and the arrows at that vertex. Now we are working on 6 vertex model. They are all the same. So okay, let me write that. So what is the weight of this? If this is I and j position, what is the weight of this? It's a horizontal thing. So it's xi over yj, right? The weight of this. And vertical molecule corresponds to this configuration. The weight is inverse of this, yj over xi. And the other things, what is the weight of this? So you can think of this as this diagonal thing or the opposite. Again, these diagonal things, we have weight az, so a xi over yj. What about this thing? So two arrows, incoming arrows are like that or like that. This we have weight xi over yj. So the weight of each vertex is defined like that. Now, how can we show that it is symmetric in these variables. So they are, if you can show xi's, then this is the same because they are really symmetric. X's and y's are by the same way we can prove the same thing. So we will prove that Zn is invariant under exchanging xi and xi plus 1, just adjacent variables. If we can show this, then because any permutation of the variables can be obtained by switching adjacent variables several times. So this will be enough to show that it's symmetric in the variables axis. All right. This is our goal. So there's a very interesting idea to prove this. The idea is, so just imagine this 6-vertex model grid. So we have n squared vertices and arrows, incoming and outgoing edges, many arrows, and we have weight. But in each row and each column, we have like each row kind of corresponds to xi, right? So think of this as this row like xi, and this vertical column like yj. And if you have a vertex meeting at xi, xj, the label will be xi over yj, things like that. So we will introduce a new vertex to this grid. So let's draw. So initially, this is first column. We are looking at the first column. I'm just considering a specific example. We're not interested in the other things. Here, we would have this every arrow here from the left, they're all incoming arrows, like that. But we're going to introduce a new vertex here between the ith row and I plus first row, and then put on arrows like that, strangely. And then what is the label of this? Let's use red. What is the label of this? This is I and first. So the label of this is xi over y1. Can you see? Yeah. The label of this is xi over y1 because it's ith column, ith row, first column. What is the label of this? xi plus 1 over y1, right? The label of this, so it's a newly introduced vertex. We're going to label this by xi plus 1 over xi. Just definition. So think of this this way. So we have kind of a curve that goes like that. Say that the label of this curve is xi plus 1. The label of this is xi. And this is xi minus 1. The label of this is xi plus 1, or I plus 2, etc. So these labels are kind of exchanged by introducing new values. So whenever so we have y1, y2, etc. So whenever you have a vertex, which is an intersection of like this curve and this curve, then we get the label for that, right? So you should think of this as like this curve has weight xi plus 1, this curve has weight xi. So what is the weight of this? It is the intersection of x1 and y1, so x1 over y1, things like that. Here, n plus 1 over y1. What is this? This is a horizontal. Think of this as a horizontal thing, and this is vertical thing. Then xi plus 1 over x1. It also consistent with that definition, right? I just introduced a new variable, a new vertex, and define the weight like that. The other weights are really the same as before. This is a trick, which is kind of interesting. Let me write this down in the description. Introduce a new vertex between ith row and I plus first row with weight axi plus 1 over xi. In other words, the label is xi plus 1 over xi. Because here, rotate this like 45 degree, then this new vertex looks like this, right? And this corresponds to xi plus 1. This corresponds to xi, so it is really the same. It really meets the definition of the weight. Okay. This may be a little confusing if you haven't seen this before, but I'm telling you, this is a very interesting idea. So try to understand. Ask me if you have any question. Okay, let's see if I can. So what now? We didn't really do anything. I just introduced new variable, except this vertex. It's exactly the same as before, right? Except this vertex, exactly the same. So what we are going to do is that we're going to move this dot across this vertical line. How? So here, the next step is move the extra dot, extra vertex, across the vertical line. So we're going to move this line like, so I'm going to copy this. Bigger picture. And we're going to keep most, so this dot will be now over here because we move this there. So, and other things will have the same orientation. Like, I'm going to copy the same orientation except this. And also, what about this? It's going to be like that. Oh, no. This becomes this. This is what I did. Maybe very, very strange. So what did I do? So here, when we move this dot across the vertical line, we're going to maintain the directions of the arrows incident to the vertices of the triangle. So we have a triangle, like this triangle now it becomes like this triangle. It's vertices of the triangle. And what about the label? And then we're going to switch the labels of the top and bottom vertices of the triangle. Move the triangle. So what is the label here? They are the same. So, you know, this is xi minus 1, this is xi plus 1, xi plus 2. So the label of this is the same as before. How can I say xi plus 1 over xi. What about the label of this? Because actually this one comes naturally if you think of this as the line labeled xi plus 1, I plus xi. So xi, y1, so the label will be xi plus 1 over y1. The label of this, xi over y1. This is what I mean. So here originally we had xi over y1 and xi plus 1. Now they are switched. And I kept the orientation of the arrows. So for instance, this one, if you look at this part, this is the arrow coming in to this vertex from the west. So it's the same, like that. What about this? This one is the arrow going out from this vertex. This is still an arrow going out from this vertex to the left, to the east. That's what I meant by maintaining the directions. So, but I haven't decided yet the orientation of this triangle. I'm talking about that later. I just changed everything here to this. I just maintain the arrows incident to vertices, to the vertices of this triangle, except the edges on this triangle. Is this clear how I obtained from here to here? Any question?
바깥에 외부에 좀 안 해줬잖아요. 근데 그 화살표에 무슨 의미가 있다는 거예요?
요 화살표?
그러니까 저 안에 삼각형 화살표 방향이 있다고 했잖아요. 그 방향에.
So these arrows are fixed. So because we have many different situations here, and we want to keep most of the information so that they have some nice relation. I'm keeping the arrows here. As I'm going to keep as many arrows as possible. I don't want to change the direction. Okay. So basically the idea is moved this triangle, or what can I say? This triangle now moved to this triangle. But so here, this triangle, we have how many edges attached to this triangle? 6. Because here we have 1, 2, 3, 4, 1, 2. The 6. This will become this. Like still we have 1, 2, 3, 4, 5, 6. And this arrow will have the same orientation as this. So this arrow, so sigma 1, sigma 1 is the same as this sigma 1. Sigma 2 is the same as sigma 2, etc. Sigma 3, etc. So here, this arrow becomes this. Orientation is the same, right? This is incoming arrow, still incoming arrow, right? What about this? Outgoing arrow. It's outgoing arrow like that. So basically, I'm going to keep this orientation of these 6 arrows like that. So sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. I just kept these 6 arrows like that, the same orientation. If you see, you can find it. So this is equal to this. This is equal to this. This is equal to this. This is outgoing, 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 incoming, incoming, like that. I just kept the 6, the directions of the arrows incident to the triangle, like that. But I haven't decided yet what the part of the orientations of the arrows on the side of the triangle. Any other question? Question? Yes, so these dots now is over here, but these two dots are the same. Okay. I think it's right. So, all right. This arrow is the same as this arrow. So this arrow eventually goes into this. So maybe that's not a very accurate, but okay. Imagine this dot. Suppose there is a dot over here. This is a dot that is somehow between this and this, but in the middle. That's now again already still between this and this. Yeah. Yes, the other vertices have exactly the same. So except these three vertices, other vertices don't even know the change. If they only look at their neighborhoods, they are the same. For instance, this one, maybe you can see, okay, this is changes slightly like that, but it doesn't really matter. They are really the same as far as the weight is concerned, right? Except these three and these three, the remaining vertices, they don't change the weight. Only the weight here will be changes slightly. Still confused? And I know this is not an easy thing to understand at first sight. I also was listening to the lecture of this like 10 years ago, and I didn't understand that at that time. So feel free to ask more questions if you have. If there's still something unclear. I need to proceed more, but yeah, I want to stop for a moment and so that you can understand. Now just change this thing like that. So how many possible assignments are there for this triangle? So because I haven't decided yet how the arrows of this. We still have this condition, 2 incoming arrows, 2 outgoing arrows at each vertex. So if you look at this triangle, here 1 coming in, 1 going out. So we must have 1 coming in, coming out, going out. So actually you can see there are 2 possibilities for this. Okay, let me rewrite this. So there are, in this case, 2 choices for the orientation of the triangle. So originally we had I'm just listing these 2 choices. This or, so these arrows, the arrows outside the triangle were fixed like that. So you can go either this way or the other way around. You can see, you can check that these are all possibilities. So what is the weight here? So let's use blue color for the weight. This is always xi plus 1. 라인이 잘못됐어요? 1. 그러네. Yeah. Thanks for the correction. That way. Okay? And here the weight is now changed. Okay, so what is the sum of the weight? What is the weight sum? What is the weight of these 3? Product of the weight of these 3. Here it's like this direction, right? So what is the weight? axi plus 1 over y 1. Right? And what is this? It's like horizontal thing, so it's just this xi over y1. Okay? What is the weight of this? You should think of this rotated that way. So it's like this. So the weight is z. So this is the weight for this. Okay? What is the weight of this? Here it's like horizontal thing, so just xi over y1. And here like this, so z, bracket z. Right? And what about this? Vertical thing. So it's inverse of this, xi over xi plus 1. I think. Okay. Yeah, maybe I should have. Let's look at the previous triangle. So the previous triangle. So that one, okay. That one was like the direction was like this. Right? The weight, the label over xi, here xi over y1, xi plus 1 over y1. What is the weight of this? We can do the same thing. Here is like this thing, so az, right? For this vertex, what is this? Horizontal thing, so the label is this, so xi over y1. Okay. This one is, oh, I didn't write this down. So this thing, so just z. So xi plus 1 over y1. So this, the three vertices here have weight this. Okay? And three vertices here may have this or this. So if you add these two together, you can just compute this, and you will discover that they are the same. This is equal to the sum of this. 요거? 아, 여기? Because I made a mistake. Yeah, they are the same. They have the same label. They are the same. Yeah. Thanks for the correction. Oh, then maybe I made the mistake again over here, right? Okay. Maybe it should plus 1 and we should go away plus 1 like that. Okay? Is that right? Yeah. No. This is the same, so yeah. Yes. Now this is correct. Okay. Plus 1 and should go away. Yes. You can check that they are the same. What does that mean? What does that mean? That means the configuration here, all possible configurations here, is equal to all possible configurations here. In fact, in this case, we are only considering just one configuration, but let's see. Right. So all possible configurations for this triangle and all possible configurations for this triangle, they are the same no matter how these 6 arrows are oriented. That's Yang-Baxter, what's called the Yang-Baxter equation. Okay. Question? Oh. Okay, so let me state this theorem, and then maybe I can, if you look at this statement, they may be helpful. The theorem is the triangle to triangle relation. Or also called Yang-Baxter relation. So I'm just drawing the same diagram. So here, we change this into, move this triangle like that. So the label here is Z1, Z2, Z3, and Z2 and Z3 are changed like that. And Z1 is now here. And the orientations of these 6 arrows are like this: sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. And sigma 1 is here: sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. So here sigma 1, sigma 6 are arrows, fixed arrows. Their orientations are fixed. If this is incoming arrow, then it must be this. So I'm not going to draw specifically. It should be understood that their orientations are fixed. But we must have this condition. There are, because 3 of them must be incoming edges. Incoming, and 3 of them, the remaining 3, are outgoing. Like if you have like 1, 2, 3, then the remaining things must be outgoing like that. We must have that condition. Otherwise, we cannot have a valid configuration. Okay? Then, the sum of weights of all possible configurations on the left is equal to the sum of weights all possible configurations on the right. That's Yang-Baxter equation. For example, let's say we have the example, like initially the example that we saw. Oh, no, these are not fixed. For instance, suppose that sigmas are like this. How can you complete this? How can you give orientation so that this is valid configuration? You know, we have 2 incoming edges, so these must be fixed, right? And here we have 2 incoming edges, so we must have outgoing for this. So there is only one possibility in this situation. So here we have only one possibility, and the weight sum for all such configuration is this. And now we look at the other side here, on this side. So this arrow becomes this, and this arrow becomes this arrow becomes this arrow becomes this arrow becomes this, and this arrow becomes this, right? Now there are 2 possibilities here. We had 2 this and plus something like that. And then we just, in the previous example, we just checked that this is equal to this and this. That's one case of this, right? And the thing is, for all possible orientations of sigmas, this is always the case, always true. How can you show that? You can show this by case analysis. How many possible orientations are there for sigmas? We must have 6 incoming, 6 outgoing. So among 6, we have to decide 3 incoming edges. This is 20. There are 20 things that you need to check. But each of these, so this is one of them. For each of them, you can just prove it by hand, just check by hand, right? But fortunately, there is several symmetries here. If you consider symmetries, there are only 5 essential things that you need to check. But still, you have to check case by case. So proving this theorem by case is a homework problem. You can either use symmetry and then just check 5 things, or you can just, if you have time, you can just check 20 things by hand, or you can use a Sage to prove this. You can make some code nicely, then you can just check using Sage. But there is no clever idea here. Once you know what you are doing, all you need to do is to list all possible things and then compute weight and see if they are the same. Okay? If you have time and energy, you can prove this. Any question about this theorem? No. Because in this case, they are fixed. But we will consider, because we will move this around, sometimes they can be in any orientation. That's right, yeah. In this example, we have like, these arrows are special, but after this, now we are going to consider this triangle, and then we're going to move this to the next triangle. So this, we don't know what these orientations are. But for any possible orientation, they're the same. That is a very interesting thing. Yang-Baxter equation, Yang-Baxter relation. Any other question? This is a crucial fact that we are going to use. But notice that the labels of these two vertices are now switched. Okay? Z2 was at the top, now at the bottom. Z3 here. But this remains the same. So in this case, in this special example, we had only one configuration, but sometimes we have more than one, and you need to prove something like that. Yeah. But it's just case by case proof. Anyone can do this. All right. Is this okay? Now, let's see if you can prove the symmetry of this partition function. Now it's the fun part. By the Yang-Baxter relation. What is this? We are interested in this, right? But we introduced a new vertex, right? If you remember, okay, let me write this down. The new vertex has this weight. So this is the partition function. For a new system, we have one more variable. So it's like we don't know what these edges are, how these arrows are decided. We don't know. Okay? But the weight of this is always fixed like this, because we have two incoming edges, so we must have 2 outgoing edges. So this configuration for this vertex is fixed. So, but except this vertex, if you just ignore this, this is exactly the same as the this partition function. So the partition function of this situation will be this times this. Okay? Oh, yeah, this. Okay? So, but now what? The equation said that you can kind of move around this partition function for this system is equal to the partition function for this system. Right? This is equal to this. Just think of this as xi plus 1, label xi plus 1, xi. Meaning that this was before xi over y1, but now it's like xi plus 1 over y1. It's the same. This, if you consider all possible configurations for this, it's the same as, the weight sum is the same as this. Their partition functions are the same. The systems are slightly different, but the weight sums are the same. Is that okay? Now what? You can just keep moving this. Now look at this triangle and then move this to the next line. Then this is equal to this. Then you can keep moving this all the way until you finally make that exit from the left, from the right. Like that. Like that. But we know that these are fixed. Like that. Okay? So again, this has weight like that. But what is the weight of this? If you look at this part, except the additional vertex, this is exactly the same as this. This is equal to Zn x y a. And what is the weight of this? This is fixed. So this is vertical line, and here it's the same. It has the same thing. So it has. They look a little different, but they have their weights are the same. Right? Oh, wait, this is not correct. Because now xi plus 1, xi plus I are fixed, switch it. So this is not this one here with xi, exchange it with. So you can cancel these two things, and we just obtain that this is equal to this, which is kind of amazing. We introduce new variable, new vertex, and you move around this vertex, and then at the end, this is kind of a magic, right? So this proves that Zn is symmetric in all the variables, x-axis, because you can switch to adjacent things. And also, you can apply the same idea for these columns then also in y1, yn. We just proved that. Yang-Baxter equation, relation. So this is the lemma that we are going to use.
처음에 엑스트라 포인트의 방향을 정해가지고
네, 네.
맨 마지막에 방향을
이거는 왜냐면 얘네들의 엣지들이 다 고정되어 있기 때문에. So like these arrows are fixed because we are always left arrows over here and right arrows over here. So they are fixed. So if the vertex is all the way to the left, it must have this configuration. Also for this, they have the same weight. These extra vertex have the same they have the same weight. More question? Oh yeah, that's right. So sometimes we have more restrictions, but doesn't matter. Because we consider all possible configurations here. No matter how these possible configurations are, they will be the same as the weight sum over here. Because we proved in this lemma, in this theorem, they can be anything. Sometimes they are fixed. So you consider just those fixed things, but still they will be the same as things over here. If some edges are fixed over here, they will be fixed over here. For the same reason. So this theorem just is enough. Is that clear? Okay, so now what? We just showed that it's symmetric in x1 up to xn, y1 up to yn. Now we can prove this theorem. So theorem, let me state the theorem again. We need some computation, but this is also an interesting thing. IJ. Okay. This takes a lot of time to write down just the formula. J, Y, I, and determinant of this matrix. Like the n by n matrix. We want to show this, proof. So let's say this part, the right-hand side, we define this to be F, and then we need to show that F equals Z. Okay? We prove this. We prove Fn equals Zn by induction on n. Okay? We're going to prove this by induction. So initial case, n equals 1 or n equals 2 can be checked. Initial case is easy. So we can check. So n equals 1 and 2 can be checked. Now we are looking at this inductive argument. So you can change this. You can by removing these brackets, you can rewrite Fn this way. Some constant, and I, J, N. XJ. So this is just computation. And determinant of 1 over yj squared a squared xi squared minus yj squared. Like that. Okay? Now what? Look at this part. This one, is anti-symmetric in the variables x1, xi's, right? If you change xi, xj, because x is like an index for the rows, so determinant changes the sign. So anti-symmetric in x1 squared. Like, think of x1 squared, xi squared as just one variable. The anti-symmetric in xi squared, and anti-symmetric in yj squared. So if you divide this by this and this, then this part is going to be symmetric polynomial. We know that if you divide anti-symmetric polynomial by Van der Waals determinant, that's going to be a symmetric polynomial. Do you remember that? We learned that. So this part is symmetric, and this part is already symmetric. So it's a symmetric polynomial. This is symmetric polynomial in x1, xn, and y1, yn. If you permute x1, xi's, you don't change the polynomial. If you permute y's, you don't change the polynomial. So it's symmetric in x1 up to xn, and symmetric in y1 up to yn. And now, let's think about this polynomial, x1, okay, n minus. So we're gonna think of this as a polynomial in x1, just one variable. We're gonna focus on one variable. So let's delete this part by multiplying this. Fn. This is a polynomial in x1 squared, right? Because this is a polynomial in x1 squared. And if you multiply this, this will cancel. So it will be a polynomial in x1 squared. Is that okay? What is the degree of this? Can you compute the degree? Maximum possible degree for this? So what is... okay, how can you compute the degree? Here we have some cancellation. Just focus on x1 squared. Here, how many x1 factors do we have here for x1 squared? I equals 1, we have linear factor for x1 squared, right? And there are n minus 1 of them. Here, how many x1s do we have? 2 x1 squared, I equals 1, I equals 1, and j can be anything from 1 to n. They are different. So here we have 2n power of x1 squared. What about this? n minus 1 power of x1 squared. But we have to divide something over here because it's the denominator. But in the first row, this first row is the only time we get some fraction where we have x1 squared. But there's only one such fraction, 2. So here we have in the denominator, so the power of x1 or degree could be, this will divide the power of this will divide x1 squared by minus x1 squared. So the degree, possible degree is 2n minus n minus 1 minus 2, which is n minus 1. So maximum possible degree is n minus 1. All right? Okay. Now what about this? Zn. Okay, let me go back to this. Consider Zn. We are focusing on x1. So x1 can only appear because this is the partition function. X1 can only appear in the first row, right? X1. And how can I say? The first row has one vertex because we have exactly one horizontal molecule, one vertex of weight. If we have something like this, then the weight will be x1 over yj, if this is in the jth column. Okay? And we already saw that here they all have the same, they are fixed. In the first row, they are fixed. And they have weight, the other vertices have weight either, they are all zeros, either x1 over y1 or ij for some j of this form, x1 ij. What is this? You can compute this, a over, this is computation. Then this part, we are focusing on x1, the degree, because we are interested in the degree. Okay. All right. So in the denominator, this is constant, so don't worry. So y's are constant. x1 we have this, x1 we have this. So if you multiply, so how many vertices do we have? Except this one, n minus 1. So we have n minus 1, x to the n minus 1 in the denominator. But this will cancel one of them, right? So we have n minus 2 x1 in the denominator. So if we multiply n minus 2 to this, it will be a polynomial. Now x is in the denominator, x1 in the denominator are all gone, and other things are now only x1 squared. So it's polynomial in x1 squared, right? What is the degree of degree what? This is the only time we have x1. For other vertices, they don't have x1. So this one, we divide this. So we have n minus 1 points there. So the maximum possible degree is n minus 1, as before. Okay? Any question? Equal? If equal is true, less than or equal to is even more true. So yeah. All right, so now what? Let's say P1 x1 equals x1 n minus 1, and this one z n P2 x1 f. Our goal is to prove that z equals f by induction. So if you can show that P1 equals P2, then we are done. They are polynomials, so these are polynomials in x1, so these are polynomial in both x1 squared of degree n minus 1 at most. So now we have two polynomials of fixed degree, fixed possible degree, n minus 1. And if we can find n variables or n numbers for which these two agree, then they must be the same as polynomials. In other words, if you find n distinct values of x1 squared such that p1 x1 equals p2 x2, then they are the same as polynomials, right? Because n, a polynomial of degree n may have at most n distinct roots. If there are more than n distinct roots, if there are more roots than the degree, then the polynomial must be 0. That's what this is equivalent to this. If there are n distinct, must be S1. If there are n distinct values of x1 squared satisfying this, they must be the same as polynomial. That's what we're going to approach. Oh yeah, that's right. n minus 2, n minus 2. Thank you. Other question? We're going to find n distinct solution to this equation. How can you do that? First, we will find one solution. Everything needs at least the first step, right? So let x1 be y1 over a. And then see if this is a solution. And consider the vertex at 1, 1. What is that? So these two arrows are fixed, right? Because it's 1, 1. These are all to the left, to the right, and these are all up arrows, right? So these two are fixed. So there are two possibilities for this. Either we have this or the other way, right? There are two possibilities. What is the weight here? It's like this. So it's AZ. So it is AZ. Z is x1 over y1, right? What is this? It's 1, which is 0. Right? 1 minus 1 inverse is 0 in the numerator. Denominator is a minus a inverse. It's non-zero. A is general variables. So this is 0. What about this? Here, if we have, it's a horizontal molecule, so the weight is z. So z is x1 over y1, which is 1 over a. So the weight of this equals 0 means that we need to consider only this. We can ignore this because the weight is 0. So we only need to consider this, okay? Because this will give just 0. The weight is the product of the weight, so we have already 0, it's nothing. Now what happens if this is this? But you know, if you remember, this corresponds to 1 in the alternating sign matrix. If we have 1, these are all fixed. We have this part, another alternating sign matrix of 1 less size. Okay? So in the 6 vertex model as well, we have fixed things. So they are fixed. They have to be oriented like this. Then they have to be oriented like that. 1, 2, 3, 4, 1, 2, 3, 4. We don't know what these are. And of course, they go like this. Okay? We don't know what this is. But this part is one smaller size n minus 1. Okay? So what is the weight of this? Here, if you look at this part, we know what these weights are. except this one. So here the weight is 1 over A. We computed this over here. What is the weight over here? This one, they all have like this direction. So Z, bracket Z. So it's going to be x1 over y2, because this is in 1, 2 position. x1 over y3, x1 over yn. What is the weight over here? They are in this direction, so it's AZ. So, oh no, same, just Z. The weight is x2 over y1, xn over y1, right? Depending on their position. So, and what is the weight sum for all possible configurations here? This is Z n minus 1, x except x1. We just delete x1. And we also delete y1. Okay. This means we delete x1 there. Okay? Because here is we have these fixed boundary arrows, and we have to fill in the arrows over here. They are just exactly the 6 vertex model with one smaller size. Alright, so what do we have now? P1. So if you plug in P1, okay, so P1, we just plug in this thing. This is equal to product of all these weights, which is y1, okay, over a n minus 2. This is just a definition of P1, and we have to multiply these weights, 1 over a, and product. What is the product of this? I not equal to 1, y1 over a, yi, xi over y1. Oh, because now I replaced x1 by y1 over a. Okay, that's what happens over here. And finally, z n minus 1. Okay. This is what we found. But we know that in P1, let's go back over here. We know that this is symmetric in the variables y. So if you change y's, it will stay the same. That means we just plug in x equals y1 a, but if you say yk over here, it will be the same, because this part is invariant. So by symmetry in y's, we get, all right, let me write this down next time. I'm just writing down the same thing with yk. And product I less not equal to k z n minus 1. We just exclude x1, but here yk is excluded because of the symmetry. And this is for P1. But by the same argument, but similar argument, we can also check. We can check that P2. If you plug in P2 there, from the formula, you can show this. You have the same thing, exact same thing. I'm just same thing except this. Now what? This is equal to this by induction hypothesis. Right? So they are the same. So yk over a is a root of P1 x1 equals p1 x2 x1 p2 x1. But k can be anything from 1 to n. They are different. So we just found not only one, but by the symmetry, we just found one thing, but by the symmetry, we found n distinct roots. That means p1 equals p2. And finally, zn equals fn. So the theorem is proved. So the crucial fact is the symmetry, because it is very difficult to find n distinct roots. But by using only one and using the symmetry, we can generate all distinct roots necessary. And this is how we prove this theorem. There are many computations, so maybe it looks complicated, but the essential, if you only focus on the essential ideas, it's a very interesting and beautiful idea. So, any question? Now we know that this partition function, and you can use this partition function to prove the ASM conjecture, and it is outlined in the exercises, so there will be the homework for the next week. And in the next week, we will try to consider refined ASM conjecture. We need to learn more to do that, but yeah. Still, the idea is kind of this line, on this line. All right, then this is it for today. Thank you for your attention.